Hey guys, here's a new tutorial covering GI. I promised this tutorial quite a while ago, but I've been busy with some stuff, and I finally got around to making this. And so this is actually supposed to be a partner tutorial that goes along with a unified sampling tutorial, since they kind of go hand in hand. And in the unified sampling tutorial, I just was talking about the unified sampling engine, the adaptivity, so all this stuff. And right now I'm just going to leave all these settings the same. So we're only going to focus on the GI and the differences between BruteForce, secondary, primary, all that stuff. And I'll lightly touch on how to adjust your memory just for tweaking purposes for extra speed and stuff. And so we're going to use the same exact scene we had, and just because this is a good testing scene so you could see noise and corners and get little nuances so you can notice them easier on big flat surfaces and whatnot. And so just to discuss the engines, just a brief overview of what they do. If you obviously have none on and you hit render, you're going to get no GI. So right now this is an interior scene, so there's only one big light right here by this window back here. And since there's no GI, it's basically just, there's no bounce light, it's just direct lighting. And so some people might say, like, why would you ever, use no GI? And actually there's situations you don't always have to use GI. If you're using an outdoor scene, like let's say it's like a big bright outdoor island scene or something, or an outdoor shot, and you're just you could just use a dome light, an HDR, and that'll cover your bases, so where you won't actually, and a directional light for example, and you won't need GI. GI will just slow your render down and you won't really notice too much of a difference. And so a lot of times for large scale brightly lit outdoor shots that are seen from a distance, so like a jungle or a forest or whatever, and you're not in the forest, you're looking at it from the outside, you could get away without GI sometimes. And so just keep that in mind. And Redshift's super fast, so I mean you could turn it on, but if you're trying to really squeeze in the speed and the quality's basically the same for your shot, then you could completely leave GI off. That's an option. Don't be afraid to do this. If give it a shot if it's an outdoor scene. And typically, since the GI engines, you have options in this. In other GPU renders and other renders that are purely brute force, for example, like Arnold or Octane, F-Storm, all these engines use pure brute force. So they're ray tracing brute force, and that's it. They don't have other biased techniques like Redshift and V-Ray have, and Mental Ray, where you can create point cloud caches that speed up the GI solving process. And so there's different situations where you might want to use brute force or Radiance cache. Photon map, I mean, this is kind of deprecated. I would never really use it, but it's there for certain situations. Same thing with the Radiance point cloud. This is great to go in combination. In Redshift, you pretty much, if you're going to use any GI for a primary, always throw on a Radiance point cloud. This will just, it's always better to just have this as a secondary. And so if we go the brute force path, like every other brute force engine out there, and we just hit render, right? So right now we have 256 brute force rays, and so there's no pre-pass cache or anything like that, and it's pretty clean. But if you zoom in, you start to notice there's a little bit of grain and noise all over the image. And so this is just an inherent problem basically with brute force path tracing. They all do this, and so the only way to get rid of this noise is you just gotta increase your samples. You just gotta fire more rays. Hence, the brute force nature of it. You just gotta push it more and more and more. And this can be problematic for interiors, because basically it's going to take way more rays to solve little dark corners like this that are a little noisier. And certain lighting scenarios, Redshift does not have bidirectional path tracing. I think only RenderMan does, and that is actually really good for certain situations. It's a lot slower, but it solves really complex, difficult lighting scenarios. But typically, you're not going to run into too many of those situations where it's like some crazy weird light setup, and you can get away with just using brute force. This is what a lot of people use. Arnold is just automatically on brute force, and so it works. It solves. It's a little slow. Took a minute and 33 seconds to do this 1080p shot, which, I mean, compared to other engines is still really fast, but for Redshift this is slow. And so you zoom in here, you check it out, and see there's like some noise, a little bit of noise, but it's basically throughout the whole image. So when you look at it as a whole, it's not too problematic. And so, but it's there, it's noticeable in spots down here. It's pretty much everywhere. And so brute force, let's just save this, is useful in most situations where it's a nicely lit shot. So interiors, brute force has a little trouble dealing with interiors, and that's about it. Brute force can do outdoor stuff, and a lot of things in Redshift are mixed. So if you change GI engine, instead of using brute force, let's say you're using your Radiance cache and a Radiance point cloud, but you have the new particle tech, particle sims, and you have hair and volumetric effects. All those things are still calculated by brute force behind the scenes. So always remember that even if you're using a Radiance cache and a Radiance point cloud, to crank up your brute force samples, because even though your whole image is mostly using your solids and stuff and refractive objects and all that are using a Radiance cache and a Radiance point cloud to speed the render up, certain elements like volumetrics, like hair, like particles, those things automatically use brute force behind the scenes. So don't think that because you're using a Radiance cache and a Radiance point cloud, you just don't pay attention to the brute force number. You want to crank this up if you're using those things. And one of the neat things about Redshift is actually you could separate what receives brute force and what doesn't. So by that I mean basically brute force shines when there's really complicated geometry, when there's like lots of little texture details and the geometry's all crazy. Think like a plant or something. It's got a lot of little details and stuff. And so what's really cool about Redshift is you can select your individual object. Let's say this was like a complex potted plant or something, and underneath the Redshift object properties, where you find your displacement information stuff, all the way at the bottom, when you check underneath the visibility, there's this option that says Force Brute Force GI. And so if you check this, basically what happens is Redshift, instead of calculating with your Radiance cache and Radiance point cloud that object, it just skips that object and goes straight into brute force. And you might want to do that in certain situations where brute force shines better, where, like I said, if it's really complicated geometry and little detailed textures and stuff. Now, a Radiance cache and a Radiance point cloud, these basically fire little it's like a cache of just tons of a little preview, I guess you could say, samples of the GI, and it kind of averages out the region. And so what this is really good for, Radiance cache and a Radiance point cloud, is when surfaces are smooth. So hence why these are great for interiors, is because surfaces are flat, walls, ceilings, floors, these boxes, stuff like that. Where and I mean, don't get me wrong, you could use this for a lot of situations, but it really takes advantage of when there's little changes in color, because the way it works is it shoots however many rays you specify. So it goes sample here, and then it says, oh, this color of GI is whatever, right? Red. And it'll say, okay, let's average this area the same color. And so you get a smoother gradient when you use a Radiance cache and a Radiance point cloud, because it's not sampling every pixel like brute force. It's kind of figuring out an average, and it just gives you a smooth result right out of the gate. And so, for example, here we used BruteForce and we got 1 minute and 33 seconds, right? And we looked at the image, we looked at it all over the place, and there's some noise and stuff, right? So I got that saved out. We're going to use the stock settings. So a Radiance cache stock and a Radiance point cloud stock. I haven't touched any of the settings. And I'll go through and kind of explain what they do and stuff. And we'll leave the BruteForce at 256. So let's hit render. Let's wait a second. And what it does is it'll do a pre-pass. So that's what this is. It's kind of figuring out the GI, and it does an average of the colors and stuff, and it figures out basically the GI without having to fire in every single pixel. And so then boom, 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 it's already solving. And so just look how much faster this already is. I mean, this is probably going to be less than 40 seconds. And yeah, we finished in 34 seconds. So from 1 minute and 33 seconds to 34 seconds. And there's a little subtle difference in spots, but overall it's pretty much the same image. Now if we zoom in and we look at things, let's check this troublesome corner here as an example. So if we go to the BruteForce, look at all this noise, tons of noise, and you check out the Radiance cache. So not only did it render faster by a whole minute, but it rendered way smoother. And the reason is because instead of the BruteForce technique, it basically just is just firing rays, and it's just going, man, what color is this? And it keeps trying and trying and trying, you know. And the only way you're going to get this cleaner in BruteForce is you just got to fire more rays until it figures it out. Using a bias technique like a Radiance cache and a Radiance point cloud, you're able to basically kind of cheat it. I mean, it's saying, okay, what's the average color in this area? Let's just, you know, why bother firing more rays in other spots when we kind of already got an average? Let's get an average here. Let's get an average here. Let's get an average. And so basically it gets to a smoother, cleaner result faster by averaging pixel color variations. And so this is why this technique shines when there's smooth surfaces. If this was like some crazy super detailed textured corner, then that might not work as well as BruteForce, because Radiance cache and Radiance point cloud like to work with smooth surfaces where there's not a lot of change, basically. That way the averages work out better. And so that's the principle behind how those point cloud cache techniques work versus BruteForce. And they both are just trying to solve, you know, what it looks like. It just so happens that Radiance cache uses averaging and thus gets to a cleaner result faster in certain situations. And so let's just go. Actually, before I run into what these parameters do, I'm going to cover the memory settings, just because a lot of people don't know what these do. And so this actually helps you speed up things. In the new 2.5 builds, you can just check off automatic, and that's all you got to do if you don't want to bother doing this yourself. And right now, the automatic memory management, it's actually really good. It's pretty solid. So you could just check it off. But to explain what they do, basically this is the percentage of the GPU memory to use. I never go over 95%. And the reason is basically, if you start putting this way too high, you could crash Maya, or you could crash your operating system. Basically, you're going to eat up too much of the GPU that you just freeze up. So don't go too high on this. I'll crank it up to 93. 93 is usually safe. And, you know, this will help you get a little bit more speed out of it. The Radiance point cloud, basically this is your caches. So Radiance cache and your Radiance point cloud cache. So let's say for this scene, 128 megabytes was enough. Let's actually, I don't know if other apps have this, but in Maya, you could click on this under System, the Show Feedback Display. And so that brings up this little window right here. And this little window will tell you all your GPUs that are currently plugged in, how much of the VRAM they have free, and how much it used, geometry. Like, okay, so for example, this scene only took up 21 KB of geometry, so I have 7.1 gigs left of cache for the geometry. Textures, it took up 0 because there's no textures. This is all just procedural shaders out of 256 capable of the cache. Matrices, sprites, there's no sprite shaders. Rays, this is basically like ray memory, that the higher you go, it's feeding your GPU more ray. I guess you could say the VRAM is loading up more of the rays being fired, so it speeds up the processes to render. This is really important. Photons, there's no photon mapping, there's no caustics or any of that stuff, so this is at 0. IC points is your 8-inch cache, so 13 megs. So it took 13 megabytes to build the little pre-pass that we saw earlier for the Radiance cache. And then the Radiance point cloud, 0 KB. I mean, it was tiny, I guess. And SSS if you're using multiple scattering. And so the cache, if your image gets really big or really complicated, what will happen is Redshift will just spit out an error saying your cache isn't large enough, it can't render. And so what you want to do is you want to go into these settings, in the memory settings, and make sure that your caches are big enough. So you could crank this up to 512 or whatever, right? Whatever number you need to get it up to so that it starts rendering. So let's just keep that back at default. And this is your percentage of texture memory to use. So like if there's free VRAM, how much of it to use, 15%, whatever, right? And your maximum GPU texture cache. So like this is really important if you're doing this manually, to crank up once your scene starts to get really complicated, when you have tons of textures, displacements, all that stuff going on, and you start going out of core. And you'll know you're going out of core because this will start to, basically what you don't want to happen is this number on the side to get bigger than the number in the brackets. See, this is 256. This is how big, once again, if we look at our cache size, 256 on each card. So if our textures now start taking up way more space than 256, what happens is Redshift goes out of core and you start to slow your render down. It won't stop rendering, it'll keep going, but you'll lose performance. So what you want to do is whenever you start to see this number go over this number, you want to increase this number to make sure all your texture space is fitting onto your GPU's VRAM. And that's just something to keep in mind. Like I said, if you're using the 2.5 builds or the newer ones, it's not out yet, but if you're using the experimental builds, you can just check this on, and you don't even have to deal with any of that stuff. And ray reserve memory, basically, if let's say, because I'm using GPUs that are, they got at least 6 gigs, and this is not taking up any space, right? So if you're using a scene that's really simple and you want to speed up your render, or your GPUs have plenty of VRAM left, that's what the rays slot is for. So what you do is under ray reserve memory, you crank this up, to whatever's realistic. So 4096 would be 4 gigabytes. It's going to take 4 extra gigs to speed up the render even further, because it doesn't need texture caches and all that stuff. So this is something you got to be careful with, just tweak it. Usually I stick to 2048 if my scene allows it. And like I said, again, you can just check on automatic memory management and you don't even have to deal with it. And it automatically does it for each card. So this is just awesome. I don't even bother with this anymore now that we have automatic memory management. It's pretty good, so I just check it and let it do its thing. So now that we tweaked the memory a little bit and turned on automatic memory management, oh yeah, and there's one more setting too. If your GPUs can handle it, if you go to Raytracing, under System, Raytracing Acceleration Structure, and you can decrease this to 4, 8, basically the larger the number or the smaller the number has performance. Larger usually means your GPUs aren't that big VRAM wise. This can be very dangerous because it could crash your whole thing. But it's stock at 8, and so you can drop it down to 4, and you'll get a little bit more performance out of it. Again, totally at your own risk. You know, if you don't want to risk anything, just leave it at 8. But this is just another thing you can tweak. Same thing with bucket size. So what bucket size is the actual little blocks, the buckets that are rendering. The size they are, stock is 128. And so how Redshift works is each bucket, it loads whatever textures, etc. it needs per bucket. So each GPU is its own bucket. That's why you can mix and match GPUs with Redshift. Unlike other GPU renderers, you can't do that because they are working on the full thing progressively. BruteForce, and since this is using buckets, Redshift lets you, each GPU is its own little bucket that's busy rendering away. So if one GPU goes out of core, that's not a problem because the rest of your GPUs are still working at their own speed. And so the bucket size basically dictates how big those little buckets are. So if you're seeing super complicated, got tons of textures, and it's just like really heavy, then it's probably better to use 64, a smaller little bucket, so that it's not loading as big of a chunk that might not fit on your GPU. For a scene like this, there's like nothing going on. It's super simple. 256 might be better, where it's a bigger block because it doesn't actually have to load anything. You know, there's just a little bit of geometry, and that's about it. And so for our purposes, we're going to use 256. And so, yeah, we got automatic memory management on, and we had 34 seconds rendering time. Let's try this again. Let's see if we get a little time shaved off of that. So let's hit render, see what happens. Oh yeah, and another thing, to save a little bit even more time, or if you're just going for a final animation render, this pre-pass phase where you kind of get a little preview, you can turn that off actually, and you won't even have to deal with visualizing it and wasting resources visualizing it. It'll just stay black until it actually goes for the final render. And so well, we didn't really get any performance change, 34 seconds anyways, but that little difference of a couple seconds can show up in more complicated scenes that are a little more complex and stuff. So, but that's just something again to keep in mind, that these options are here. And again, like I said, this scene's too simple for ray reserve memory to actually matter, for the bucket size, all this stuff. But I'm just explaining how these parameters affect your scenes. So anyways, let's get back to comparing what the cache systems do and how to use them basically. And so here's the show calculation. So if you uncheck show calculation and you hit render, let's actually just save that. And we hit render. What happens is it doesn't even visualize that pre-pass. And so it's not going to make much of a difference, like again, because the pre-pass in this scene is getting created so quickly. But in more complex, heavy scenes, that little bit of time saved rather than building a pre-pass is just, it saves you a little bit of time because you go straight to the render once the cache is ready and built. And so, boom, there it is. Oh, and see, we did gain 2 seconds. Even on this super simple scene, turning off show calculation gained us a little bit of time. So, anyways, we'll just keep it on for now so you guys can visualize the caches when they're being built. And so, there's also this option to rebuild. So, if you rebuild the pre-pass or load, so let's say you built an animation or a walkthrough or a simple camera move, and what you could do is you could build your caches so that they save out like a file, kind of like a pass, and so that way you don't have to build them every time you start. You know how it starts doing the little cache building process. It'll just be saved, ready to go. And so you'll just go straight to rendering. And so this is a good idea if you're building animations. For stills, it's kind of overkill, but if you're doing animation work and you're using Radiance Cache, Radiance Point Cloud, it's usually a good idea to use these. and just work from there. It'll save you time in the long haul. And so here's the settings for Radiance Point Cloud. Again, a Radiance Point Cloud, always use it. So if you're going to use Brute Force, try to use a Radiance Point Cloud. You don't always have to. Sometimes just pure Brute Force works, and it's just a little bit faster. But Radiance Point Cloud basically is like a simpler version of a Radiance Cache. It does a similar thing. So if you're using primary Brute Force, so your engine's doing everything Brute Force, and you have a Radiance Point Cloud, Radiance Point Cloud kind of does a little bit of the averaging, just like a Radiance Cache, but it's not taking over as much as Brute Force is. And so, for example, this is our, let's delete this. We have our original Brute Force scene. So this is the original Brute Force, and we'll try it with the Radiance Point Cloud, but we'll tweak the settings. So screen radius, basically this is the pixels in per pixel, the radius of the pixel. So 16 is like 16 pixels, and it calculates kind of like the averages of that area. That's the radius, basically, if you want to think of it that way, of the averaging process. So if you have 64 versus 16, etc., etc. So it's always a good idea, if you get lost with some of these things, check out the documentation. Documentation tells you everything you need to know, basically. So it explains what things do, how to tweak them. Here's screen radius. So if you look at this, basically, it's the like mentioned above, the Radiance Point Cloud algorithm stores points around the screen, hence the little dots you see getting cached. And for each ray of the camera, because doing so would generate an extremely large number of points for high resolution images. Instead, it uses screen space metric to space out these points. So it's spacing them out. And so, again, 16 or 8 versus 64 or whatever. And so if your image is low resolution, like they said, one of the cool things about these caching techniques is that resolution doesn't really change the quality too much. So this could be 4K and you could pretty much get the same quality out, and it doesn't increase time render as much as Brute Force, because Brute Force is creating more surfaces, basically more pixels that have to be resolved, while this kind of still averages distances. And so we're going to stick to 16 for now, because again, this is only 1080p. Samples per pixel, this is how many rays will be shot at each one of these points that it's trying to average out. Filter size, this, and retrace threshold, I never really mess with these. I'm not exactly let me see. Brute Force range cache, shoot Brute Force. So closest points the algorithm should use. Yeah, I mean, this is if you're like really trying to tweak certain little details and whatnot, like the sensitivity, basically, of how sensitive the adaptivity of color changes that it averages are. And so I don't really deal with them too much. I think the stock's pretty good. The only thing you really need to change is samples per pixel. So if we increase this to like 64, or I don't know, let's go even crazier. It's 256. And let's make sure our caches are large enough, because they're going to be more detailed. And so we have 256. Let's do a render. And so this is Brute Force primary, Radiance Point Cloud secondary. And you see it's starting to build the little point clouds. That's what all these little dots and stuff are. And so it builds your cache to help the Brute Force GI engine solve cleaner, basically. Instead of firing tons of Brute Force arrays, it kind of averages it out with the Radiance Point Cloud cache that we're building ahead of time. And so this is going to take a little longer, because I'm firing a lot more arrays. So 256 versus the 16 we had stock. And let's see. So you can see it's working away. This is probably overkill. I shouldn't have done this much. Would have been fine with 64 or something. But, you know, let's go with extreme so you guys can see what it does more. And so now it's actually solving. And so if we zoom in here, and even though this is brute force primary, if you swap back and forth, you see how it cleaned up the noise. It's a lot more blocky and noisy, and the Radiance point cloud method basically helps the brute force engine solve difficult areas of GI by averaging out the pixels. And so this is only a minute 37. The original brute force method that was pure brute force for primary and secondary is a minute and 33, and it's way noisier. So again, this is one of those situations where I tell people, it's like, always use a Radiance point cloud if you can. It will look cleaner and solve in less time if you want the same as brute force, or solve basically the same time and be a lot cleaner. And so, you know, we look around, there's still noise. You know, again, this is an inherent problem with brute force methods, but it's cleaner than just pure brute force. See, smoother color transitions and gradients right there. Pretty much everywhere, it's going to be like that. And so that's what this does. This is the only parameter really you should tweak, this and this, depending on how. If your render's like a 4K image, maybe use 64 or 32, which is the distance between pixels for every shot that it's firing. Or 16 stock usually is pretty good. Let's drop this down to, I don't know, let's try 32 instead of 16. And so that's what this is. So we'll save this out. Now we're going to try Radiance Cache as primary and Radiance Point Cloud as secondary. And I would never use brute force as a secondary. It's too sloppy to really be helping for a secondary engine. So just no point in even having it. You can have none if you want, but you know, try Radiance Point Cloud's fast. And so here we got the same options as the Radiance Point Cloud. You could rebuild or build and save it or load your already saved out caches. So this is an option. Show calculation. Again, we can turn these off and get a little bit more speed. But for now, since I want to show you guys how it's working and stuff, I'll keep these on. And visualize points. Again, this is something if you want to see more of how the little points are being built and whatnot. And stock settings. So this is all a bunch of parameters. You can use the presets. Low is, you know, it works pretty well actually for a lot of situations. Medium, high, custom. I find that custom just without even touching anything usually works pretty well. But let's just stick to custom stock. So I'll explain what the minimum rate, max rate does and whatnot. So minimum rate, basically -3 is like how the Radiance cache is working. It's kind of making a snapshot of this render. So this render is 1080p, right? And so let's bring up a calculator. And so what minimum rate does, if you do minimum rate -1, for example, it's going to be basically your 1080p render, right, divided by 2. And so it's 540. And so what it does is it averages out your render. So it's shrinking it down. And it kind of uses that information as minimum, like the averaging of a low res version of this will be your minimum. So let's say that your thresholds are saying, oh, it's clean enough. It'll use that lower res version. And so if you do a minimum 3, that's really low res. And it just uses the average colors of what's there. Max rate, it's basically the opposite. Max rate is how much, if it needs a detailed quality approximation of this image, it'll do that. So 0 basically means a full 1080p, the full quality of the image. Plus 1 means a double this image and whatnot, you know, and as you keep going up the scale. And so again, you can find this information here where you check this out. So minimum max rate. And so -5 means divide resolution by 32, etc., etc. -1 divide resolution by 2, and so forth. And so this is important because this basically kind of dictates the resolution of the initial quality of the caches that are being built. So keep this in mind. Color threshold, again, this is similar to the thresholds for the Radiance point cloud, where it's basically saying, you know, how much to average out. So it goes into detail here about the distance, the normal thresholds, and whatnot. But if you want to just sum this up, it's basically how sensitive it is. How sensitive it is to, like, oh, there's this corner, and, you know, the color changes from this dark reddish to pink over here. That's the sense. It's the sensitivity to those changes, and how sensitive it is. Distance threshold, same thing. Normal threshold being like angles like this. So right now it's on high, so it's sensitive to realizing this is a corner. So again, I usually leave all this stuff on stock. It's, I mean, you could tweak it, but it's not. Usually it's pretty good stock. The most important things you need to tweak basically are the number of arrays, again, just like samples per pixel, and the minimum max rates. And so for our purposes, we'll do -5, just so you can really see the difference, and a -1. And we'll drop the rays down to 300. So this is going to build the Radiance cache super fast, but it's not going to look as good so as how stock was. So let's just hit render, let it load up. And by the way, one of the things about a Radiance point cloud and Radiance cache is for animations that are really complex, they're not that good. So for animations, you want to go BruteForce primary, just when there's a lot of stuff going on, and that's just because BruteForce handles animation changes and camera moves and deformations and all that stuff a lot better. And a Radiance cache and Radiance point cloud can get splotchy, and so there's a certain point where, yeah, you could tweak the settings to get rid of it, but it might take too long to render it versus just going BruteForce all the way. And so there's those situations where that's, you know, it's better to go with that. For simple kind of like fly-throughs, environments or stuff, you can get away with the Radiance cache or Radiance point cloud. But when it's complicated character, fur moving, motion blur, all that type of stuff, you might want to just stick with BruteForce. And so here's our render. It's still rendered in 30 seconds, and it's still super clean. I need to drop the settings even further, I guess. So let's actually drop that number of arrays to just 50, something ridiculously small, and -3. Or let's just go low. No. Yeah, let's just stick to custom. Let's go -5, or -6 even. -3. Yeah, let's try this. And so I'm thinking my Radiance point cloud might be too high, that it's actually helping smooth it out. So actually, let's cancel that. Let's turn that off so you can just see the difference with the Radiance point cloud by a Radiance cache by itself. And so we're not getting as much bounce actually because there's no secondary. So let me turn on BruteForce. Let's try that again. And this is exactly what I said don't do. Because BruteForce is just not really a great secondary engine. But whatever. And so it's built, right? The cache is done. It did its thing, rendered in 19 seconds. And so if we zoom in here, I mean, it's noisy. It's noisy everywhere. There's like a little weird, like a snow, like a static almost, all over the image, and weird splotchiness. And that's because it's averaging out stuff, and it's just not, the cache isn't detailed enough, you know. It's using a low res -3, so it's dividing by whatever it was, 3 times or whatever. And so it's just not high quality enough. And so it's rendering faster, but I mean, you could see big old splotches everywhere. And so to get rid of that, again, let's go with at least 0. Or we'll do a really clean one actually. So let's do 1. So it's doubling the image size. And our minimum we'll go with -3. And that's all we'll change. We won't change the number of arrays yet. So let's save that out. Let's hit render. And so this is taking a little longer to build. And you see how this is the averaging basically. These little blocks are the average color that's there. And so that's how it solves the information faster. And so, okay, cool. It rendered. But we still got this like weird blotchiness going on. And but they're smaller this time. And the reason they're smaller, these little blotches, is again because we increased our minimum rate so that the image that's being sampled is larger, and we increased our max rate so that it decreased the splotchiness. But obviously you can still see it everywhere. It's kind of like this weird, I don't know, like a gobo effect. And so only way to get rid of that now is pretty much increase the ray count. So if we increase this, I mean 50 is tiny. This thing comes stock 2000. You don't even 2000 sometimes you don't need. So we'll just go 500 and we'll hit render. And so it's taking a little longer to build. And you can see how it's a little more, basically it samples the color a lot more, 500 times this time instead of 50. So it gets a better idea of what the color is. So you see the averages now are more consistent. And so you zoom in here, and I mean, there is a little bit of splotchiness here and there, but the averages between each sampled region are basically a lot, they're defined more. So it reads as a whole a lot smoother. And so again, we could increase this to 2. Decrease this to 2, and so this is going to make our little sampling regions even smaller. Instead of 500, we can go with 700, and let's hit render. And so you can see that it's firing way more little dots. These are sample regions where it averages the color around. And so it's taking longer, obviously, to build. And as you can see, let's zoom in here. These are all the little regions where it's averaging the colors together. And so, yeah, as you can see, it took a little while to just build the cache. But it's going to be a lot smoother. Like a lot. And so if we zoom in here, I mean, we have this super smooth versus this big blotchy blocks versus BruteForce, which is way over here. So BruteForce, Radiance cache, Radiance and no point cloud. This isn't even with point cloud yet. And so, again, that's overkill for a scene like this. I don't think you'd need that much. But that's how you get rid of splotchiness, basically. You have to decrease the sampling size that's being sampled. So your minimum rate has to be increased, and your max rate has to be increased, so that way your sample regions shrink, because it's using larger images to sample from, larger cache images, basically. And the number of arrays basically just makes it so that it calculates the sample regions better, because it's firing more samples at that region. So it figures out, you get a smoother gradient, basically, because the sample here versus the sample here will be closer alike because it figured it out better. The calculation was done better. And so let's turn this back on to Radiance point cloud, and let's drop this back down to 3. We'll keep this at 2, 700, 32, and we'll save this. So instead of using brute force now, we're going to use both the cache methods. And I actually dropped down this one because I think it'll still be overkill. So let's do 1. And the number of arrays is 700 instead of the stock 2000. And this is 32. So let's just see what happens. And so now that we're using both methods for the GI, to basically, both methods average out the calculations of GI instead of firing samples. Again, the brute force method is brute force, hence the name. It fires at every single pixel, and it's firing, trying to solve, and so it takes longer, and it gives noisy results. That's how you get fireflies. That's, you know, all those situations, because it's trying to solve more pixels, and some pixels might be too hot, and that's why you get fireflies. That one random pixel that just caught a weird specular highlight. And so this took 40 seconds, and we zoom in, and I mean, this corner right here is even smoother than the last one, and way smoother than brute force. And the only reason, again, is because we're using these cache techniques, and it's smoother even than the secondary with brute force. And the reason, again, is because of the Radiance point cloud. And so this becomes useful if you're going to do a 4K image or something. So let's just say, for example, okay, this took 40 seconds, and we're going to double the res. So we're going to go, or not double it, but we'll go 150%. Actually, no, yeah, that might take too long. I don't know how long it'll take. Let's go 150% larger. And so we're going to render this, and let's see what happens. My cache might not be large enough, but I don't know. We'll find out. If this thing triggers a warning. Oh no, it looks like it's going. It'll let you know. This thing will basically turn red, and it'll give you an error down here saying your cache for a Radiance cache or a Radiance point cloud wasn't large enough. But it looks like it is. And so it's doing its thing. It's rendering. And keep in mind, this is 150% bigger, so you know, it should, in theory, right, like other render engines, if you use brute force, when you make that much bigger of an image, it should be a lot slower, because you're sampling so many pixels again, you know. But not so. With Radiance cache and Radiance point cloud, you can increase your image size quite a lot, and you won't lose any quality. You won't. It just, because it's averaging, and that's the beauty of it. That's the beauty of the bias technique. It's averaging areas out instead of having to solve all the way. So 1 minute and 15 seconds. You know, it's still faster than the 1080p brute force. The 1080p brute force was 1 minute and 33. And I mean, let's zoom in here, and it's still clean. You know, I mean, just think about that. So let's, just for comparison's sake, we'll use this higher resolution, but now we'll just change it over to pure brute force. We're going to see how long this takes, just to see, and how much grainier it is. So let's see what happens. My prediction is it might hit 3 minutes, and it'll be quite a bit noisier than this one. But I don't know, we'll see. Maybe it won't. So let's zoom in here and see how it's doing. And so, looks pretty grainy, but let's swap. Oh yeah, way grainier. By a lot. As expected, because it's brute force. And it's still barely here. I mean, yeah, it's going to take a while. Let's see. And so again, just to recap, since I'm going to end the video pretty soon. Brute force, brute force. This is what other engines use. Arnold, F-Storm, Octane, V-Ray RT, progressive sampling, basically. And it works it's great for animations. It's great for complex, detailed shots where things are really textured and detailed. But it has trouble in difficult lighting scenarios like this, interiors, cleaning up noise, and whatnot. But keep in mind that you can use Irradiance Cache, Irradiance Point Cloud, and turn on brute force for specific objects. So if you have complicated objects that need it, turn that on. And something else to keep in mind is you don't always need a GI engine. You can sometimes go with none. If it's an outdoor scene with a nice HDR and a directional light, that's all you need. No need for GI, because it's being lit nicely from all angles, basically. And Irradiance Cache and Radiance Point Cloud, these are the two biased cache techniques. They're great. They shine really well when there's smooth surfaces that aren't changing so much, so that the averaging of each region that's sampled works. And there can be splotchy issues, like I showed earlier. So yeah, this finished at 2 minutes and 44 seconds. About, what I guessed at. A little under 3 minutes. And then this was 2 minutes and 15 seconds. And they're nearly identical. The main difference being the noise. The noise. Look at this. Noise. Tons of noise. Way smoother. Noise. Smoother. Noise. Smoother. So yeah, I'm a big fan of Radiance Cache and Radiance Point Cloud. Basically, that's the beauty of Redshift. It has all these biased tricks where you could shave off time and get a cleaner render as long as you take advantage of them. If you're not taking advantage of this stuff, then and you're just going pure brute force with everything, you might as well just use something else. Otherwise, do try to learn what these parameters do. Do try to take advantage of what a biased engine has to offer. It might not matter much for a still, but the difference, that 1 minute difference between these two and the better quality in the Radiance Cache version adds up to hours in an animation, So just keep that in mind. So again, Radiance Cache, Radiance Point Cloud, great for flat surfaces, interiors, architectural stuff that isn't super complicated, like some crazy aerial jungle shot or something. You don't need this, You stick to brute force, but always try to use secondary Radiance Point Cloud. Radiance Point Cloud's great. It helps smoothen out the noisiness of brute force if you're using brute force as your primary method. Always remember that brute force, even though you're using Radiance Cache, Radiance Point Cloud, that brute force GI still affects volumetrics, hair, particles, and a couple other minor things. So keep this in mind. Don't just forget that this is even here and leave it at like the stock 16 or whatever. Another thing to keep in mind for Radiance Point Cloud and Radiance caching is you could save those pre-passes so you don't have to deal with them later. Great thing to know. Another thing, show calculation. Uncheck these. If you don't care about visualizing it, just keep them off, and it'll render a little bit faster. Screen radius. Screen radius on Radiance Point Cloud is basically the same idea that's going on with the minimum and max rates. Basically, it's kind of like it's figuring out the pixel width, and that's the region of averageness. So 16 is fine for smaller images, maybe 64, where 64 pixels wide is a big enough average region. Or if you have something super detailed, go with 4, and every 4 pixels it's going to sample that area for an average. Samples per pixel, this is how many of each little dot, how many times it gets hit. So 32 is pretty good, 16 is usually plenty, but if you need more quality, maybe go up to 64. I never go over 64. 64 is, I think, already a lot. Filter size and retrace threshold, I don't really mess with these, but this is just kind of the sensitivity. It's similar to the adaptive error threshold parameter in the sense that it adjusts how sensitive the point cloud color averaging is. And so for Radiance cache, minimum rate, basically imagine this whole image shrunken down 3 times or whatever. Max rate, same image but blown up 1, so 0 is the default. And so what this does is it builds a low res and a high res sample, a quick sample of the image that it uses to average out the colors. Color threshold, similar to the filter size and all that stuff. It's just a sensitivity to the color changes. Minimum detail, same thing, except this is, I think, value changes. I'm not exactly sure. And radius factor, I think that has to do with the angle of stuff, like corners, etc., etc. Number of rays, again, this is the most important one to keep in mind, which is just like the samples per pixel. The higher you crank this up, the more times each little dot is going to get sampled. 2000 is a lot. You can get away with 700. I use 500, 700 all the time. And that's about it. The adaptivity, adaptive error threshold, again, these are the sensitivity settings. And if you're getting splotches, maybe your minimum rate's too low. Crank it up more. Crank up your max rate. And it'll shrink down your splotches. And if you're noticing the splotches more, like the colors are too random next to each other, crank up your samples so that way your samples average out nicely. And again, that's pretty much it. That's the basics to what each GI engine does, when to use it, why to use it, how to tweak it, what makes them useful. And obviously, for everyone, just stick to automatic memory management. It's great if you have this option. If not, go back to the video and check out how I explained it. But always use RAID reserve memory if you have it. If your GPUs are big enough, if you're using a Titan or whatever, 1080 Ti, 1070, throw in an extra 2 gigs. It'll speed up your render. And yeah, that's about it. Hopefully that covers GI, and keep all these settings in mind when you're tweaking your unified sampling, and you'll be able to get really fast renders, really clean, nice results without all the headache of random noise and stuff all over the image. All right, guys, have a good one.